This lecture 6 also included under impact of fossil fuel, where we will be studying regarding the ozone hole formation and its impact. So here also learning objective will be one of the impact of the fossil fuel, that is we will be talking regarding the ozone hole depletion. So directly coming to slide number 12, we have what is ozone. So we will be starting our lecture with one of the impacts of the fossil fuel, that is not only fossil fuel but another major part is due to the anthropogenic activities, and that is formation of ozone hole, or we can say the depletion in the ozone layer. So first of all we need to know what is ozone. So ozone is a molecule, formula O3, made up of 3 atoms of oxygen and mostly found in the stratosphere, where it protects from the sun's harmful UV rays. Although it represents only a teeny fraction of the atmosphere, ozone is crucial for life on Earth. Ozone in the stratosphere, a layer of atmosphere that is between 15 and 50 kilometers above us, act as a shield to protect Earth's surface from the sun's harmful ultraviolet radiation. So without ozone, the sun's intense UV radiation would be sterilize the Earth's surface. With a weakening of this shield, more intensive ultraviolet B and ultraviolet A radiation exposure at the surface would lead to quicker sunburn, skin cancer, and even reduce crop yields in plant. However, near the surface where we live and breathe, ozone is a harmful pollutant, that is in the tropospheric ozone, that causes damage to lungs, tissues and plants. This bad ozone forms when sunlight initiates chemical reaction in the air involving pollutants, particularly a family of gases called nitrogen oxides, which are actually released from the vehicles and industry during the combustion process, and with volatile organic compounds like carbon containing chemicals that evaporates easily into the air, such as petroleum products. Chemistry of the ozone layer. What happens? There are natural processes that create and destroy ozone in that stratosphere. These processes regulate a balance of ozone and that form and destroys in that particular layer. Ozone is created primarily by sunlight. When high energy ultraviolet rays, that is UVC, strike an oxygen molecule, they split the molecule into 2 single atoms known as atomic oxygen. A freed oxygen atom then combines with another oxygen molecule to form a molecule of ozone. Because there is so much oxygen in our atmosphere, this oxygen ozone cycle is continuously absorbing high energy ultraviolet radiation UVC and completely blocking it from reaching the Earth's surface. This process creates heat which warms the upper part of the stratosphere. Ozone is very reactive and attacks other molecules in the air, often regenerating oxygen in the process. Also, and this is why ozone is important to us, ozone in the stratosphere absorbs much of the sun's UV rays, especially UVB rays, splitting back into molecular and atomic oxygen. No matter how the oxygen atom is produced, they almost quickly react with oxygen molecules, forming the ozone. So while ozone is continuously being replenished, it is also continuously being destroyed. Sometimes an ozone molecule reacts with an oxygen atom, creating two oxygen molecules, thus ending the cycle. If the rate of ozone creation is equal to the rate of destruction, the total amount will remain the same. This is called a leaky bucket. If you pour water into the bucket at the same rate that it is leaking out, the level of water in the bucket will stay the same. Scientists have found that ozone levels change periodically with regular nature cycles such as changing season, winds, long time scale sun variations. Ozone also responds to some sporadic solar events such as flares. Moreover, volcanic eruptions may inject materials into the stratosphere, which can then lead to increased destruction of ozone. Human production of chlorine containing chemicals like chlorofluorocarbons has added additional factor that destroys the ozone. CFCs are molecules that make up of chlorine, fluorine and carbon. Because they are extremely stable molecules, CFCs do not react with other chemicals in the lower atmosphere, but exposure to the ultraviolet radiation in the stratosphere breaks them apart, releasing the molecules. So we have the Chapman cycle, which is actually nothing but formation of this ozone molecule, which occurs actually naturally. The stratosphere is a constant cycle with oxygen molecules and their interaction with the ultraviolet rays. This process, we considered it as a cycle because it's constant conversion between different molecules of oxygen. The ozone layer is created when ultraviolet rays react with oxygen molecules to create ozone and atomic oxygen. This process is called Chapman cycle. So what we have learned from the previous slide, that we will be seen in the form of the reaction. That is step 1. An oxygen molecule is photolyzed by solar radiation, represented in the form H nu, which actually creates two oxygen radicals. So two oxygen radicals are there. In step 2, oxygen radicals then react with molecular oxygen to produce ozone, O2 plus O, giving rise to O3. Step 3, ozone then reacts with an additional oxygen radical to form molecular oxygen, O3 plus O to O2, giving rise to two molecules of oxygen. And in step 4, actually ozone can also be recycled into molecular oxygen by reacting with a photon. So ozone plus in presence of light, what it will give rise to? Oxygen molecule and one atomic oxygen, which can again react with two oxygen molecules to give rise to ozone. So it is important to keep in mind that ozone is constantly being created and destroyed by the Chapman cycle, and these reactions are the natural process which is occurring in our atmosphere and occurring through millions of years. Because of this, the thickness of ozone layer at any particular time can vary greatly. It is also important to know that oxygen is constantly being introduced into the atmosphere through photosynthesis. So the ozone layer has the capability of regenerating itself. Now, what we are doing here, or what is the role of these anthropogenic activities? They are actually creating certain compounds which are actually interfering with this Chapman cycle. Now, what we have here is the reaction of chlorine with the ozone, because this chlorine we are actually generating through human activities. We will come into that. Now these free chlorine atoms then react with ozone molecules, taking one oxygen atom to form chlorine monoxide and leaving an oxygen molecule. So this chlorine atom, each of these chlorine atom released forms from a CFC molecule destroys only one ozone molecule. So now what happens, these CFCs would pose, if the reaction stopped here then it wouldn't be a problem, but what happens, the oxygen atom breaks up this chlorine monoxide, stealing the oxygen atom and releasing the chlorine atom back into the stratosphere to destroy another ozone molecule. These two reactions happen over and over again in a cyclic manner, so that a single atom of chlorine acts as a catalyst and destroys many molecules, about 1 lakh molecules of ozone. Fortunately, chlorine atoms do not remain in the stratosphere forever, and free chlorine atoms react with gases such as methane and get bound up into the hydrogen chloride molecules. These molecules eventually end up back in the troposphere, where they are washed by the rain. Therefore, if humans stop putting CFCs and other ozone depleting substances into the stratosphere, stratosphere ozone will eventually return to its normal values. Now, how we are measuring ozone in the Earth's atmosphere? The principle of measuring ozone is very simple. We know from measurements how much incoming UVB rays, sunlight arrives at the top of Earth's atmosphere every second. We also know how much light, including the ultraviolet B, is scattered by air molecules in the atmosphere, also called as Rayleigh scattering. And this is the same phenomena that makes the sky appear blue. So if we can calculate the amount of ultraviolet B sunlight that would make it to the Earth's surface if there were no ozone to absorb it. When we measured the amount of ultraviolet B sunlight from the ground, we find it much less than what we calculated. So the difference is the amount of ultraviolet B absorbed by ozone, and from that we can calculate the amount of ozone. The longest satellite record of ozone data has been from instruments using this backscatter method. The first measurements were taken by the BUV instrument on Nimbus 4 satellite in 1970s, followed by the total ozone mapping spectrometer or TOMS instruments in the Nimbus 7. So in one way, directly we can see what is the difference in the energy radiations. In that way we can measure, and also the unit of ozone measuring is in Dobson unit. And there is, if you want to measure the ozone from the top of the earth, that is through the satellite, there the main technique is the TOMS, that is total ozone mapping spectrometer, which is which is actually placed in the Nimbus 7 satellite. So these are the two ways which are actually, many other ways are also there, but we are talking about the two ways. So these are the two ways which are actually used to calculate how much the hole has enlarged or how much the hole has depleted, or it has rectified itself back to normal. So all these we are calculating, but the unit is Dobson unit. So how this ozone hole is formed and where we can actually find them on the earth. The ozone is not really a hole, but thinning of the ozone layer over the south polar region of the earth. Every year since at least 1978, there is a sudden, rapid decrease in the stratospheric ozone levels at the end of Antarctic winter. So, during the long winter months in the Antarctic, atmospheric temperatures drop, creating unique conditions for chemical reactions that are not found anywhere else in the atmosphere. The wind in the stratosphere over the polar region intensifies and forms a polar stratospheric cloud or polar vortex, which circulates around the pole. The transition from inside to outside the polar vortex creates a wind barrier that isolates the air inside the vortex and also results in very cold temperature. So this results in a mixture of ice, nitric acid and sulfuric acid formed in the stratosphere. Chemical reactions on the surfaces of these ice crystals convert chlorine containing compounds like HCl, which is a harmless to ozone, into more reactive form. When the sun rises over the Antarctic in the spring, that is September, light rapidly releases free chlorine atoms into the stratosphere. So a new ozone destroying cycle begins. The chlorine atoms react with ozone, creating ClO. The ClO molecules combine with each other, forming a compound called a dimer. Sunlight releases chlorine atoms from the dimer, and the cycle begins again. The polar vortex keeps the ozone depleted air inside from mixing with the undepleted air outside the vortex. So we can see the depletion of ozone layer or so-called ozone hole over the Antarctica region of the earth. Now we have certain ozone depleting substances, that is mainly CFC or chlorofluorocarbons, hydrochlorofluorocarbons, hydrobromofluorocarbons, halogens. Together we can call them as halogens because belonging to the halogen family. Methyl bromide, carbon tetrachloride, methyl chloroform. So the ozone layer prevents most harmful UVB wavelength, that is 270 to 315 nanometer of ultraviolet light from passing through the Earth's atmosphere. Ozone can be destroyed by a number of free radical catalysts, the most important of which are the hydroxy radical, the nitric oxide radical, and atomic chlorine and bromine. All these have both natural and anthropogenic sources. At the present time, most of the OH radical and NO radical in the stratosphere is of natural origin, but human activity has dramatically increased the levels of chlorine and bromine. These elements are found in certain stable organic compounds, especially chlorofluorocarbons, which may find their way to the stratosphere without being destroyed in the troposphere due to their low reactivity. So once in the atmosphere, chlorine and bromine are liberated from the parent compounds by the action of ultraviolet ray, and these chlorine and bromine atoms can then destroy ozone molecules through a variety of catalytic cycles. Uh, in a simple example of such a cycle, a chlorine atom reacts with an oxygen molecule, takes an oxygen atom from it, leaving a normal oxygen molecule. We have seen this reaction. The overall effect is a decrease in the amount of ozone because, as we have seen, single chlorine atom is able to react with 1 lakh ozone molecules. So here also, in the same case with bromine, fluorine and iodine, they also do have the capacity to react and produce or break down the ozone layer. But bromine is more efficient than chlorine, but there is much less bromine in the atmosphere at present. So laboratory studies have also shown that fluorine and iodine can also participate in this ozone depletion layer. But fluorine atoms react rapidly with water and methane to form strongly bound hydrofluoric acid, while organic molecules which contain iodine react rapidly in the lower atmosphere where they do not reach the stratosphere in significant quantities. So these are the reasons and consequences of the ozone layer depletion. As we have seen, ultraviolet B rays reaching the earth, and there is an increase in the probability of cancer, mainly skin cancer. And to our knowledge, the World Ozone Day in 1994, the United Nations General Assembly voted to designate September 16th as the World Ozone Day to commemorate the signing of the Montreal Protocol on that day in the 1987, which deals with reduced use of ozone depleting substances. So that was the treaty in the Montreal Protocol, that the countries responsible or signing the treaty will be reducing their use of ozone depleting substances.